Hey everybody, I wanted to clarify some things about phase two of the project that you might be confused about. I'm just going to try to do a short video here. This is my first video. We'll see how it goes. Um, so I'm going to be referring to the document that's already on Canvas here. The project phase two, it's a partial solution. It's not the whole thing. It's the part that you've already submitted to us. So if you click on that, and I already have that open here. Let me get that brought up for you. Okay. I'm just going to focus on free body diagram exercise number 3 because I think this pretty much summarizes everything that you need to know, and this will really help you get started with solving the problem. So looking at this, basically I want to make sure you're clear on how to do a free body diagram in general. You're basically doing a force inventory. So you basically want to think about what is in contact with the object. In this case, the object's a car. So first of all, you're always going to have a weight force. But then the only other forces you can have are ones that arise from things actually touching the object. In the case of a car, you only have two things that are touching the object. You have the road underneath and you have the air around it. So let's focus on the road underneath first. I'm going to try to annotate this a little bit. Okay. So again, you're going to have weight force always, and that's the only force that you get due to something not touching the object. All right. Besides the weight force, as I said, we have the road in contact. So you got to think about all the forces that you could have due to the road. And of course, one of those is going to be the normal force. You always have a normal force when an object's in contact with the surface. And then you're usually thinking about friction forces. In this case, because we're dealing with a rolling object, because the tires are squishy, you're going to get this rolling resistance force also. We don't normally deal with this in this class, but because vehicles are so heavy and because the tires are relatively soft, you're going to get this opposing force. The key thing you have to remember with the rolling resistance force is that it always opposes the motion. It doesn't matter if the car is going uphill, downhill, constant speed, speeding up, slowing down. All of those scenarios, this rolling resistance force is going to oppose the motion of the car. So if the car is moving forward, the rolling resistance force points backward. To get its magnitude, that's up here in the table. We calculate it very similarly to the regular friction forces. You're given that mu RR value is in your specification table. So you can get that from there. Normal force is calculated the way you normally would. Never assume that it's equal to weight force. In fact, in this case, it's not. Always get that from free body, or I'm sorry, from Newton's second law. So yeah, again, to summarize, rolling resistance always opposes the motion, and the magnitude is calculated from here. The other force resulting from the road touching the car is the friction force. And we're used to friction force opposing the motion or opposing the intended motion. In the case of a car, it's a little different because you have the wheels underneath of it trying to make the car go. So this is kind of one situation where we're not really thinking of the entire car as just a particle. Most of the car is, but you have these spinning wheels underneath. And because when the engine's trying to drive the vehicle, because the bottoms of the tires are trying to push backwards, you're going to get a force pushing forward. So in other words, when the tires try to spin backwards on the road surface, the tires will apply a force to the road that's backwards, and because of Newton's third law, the road will apply an equal and opposite force on the tires. So a backwards force on the road results in a forward force on the car. And that's the force we show in the free body diagram. We're only worried about forces on the car itself. So any forces on the tires, forward or backward, are going to be shown on the free body diagram. So this friction force is going to come from any of the tires that are trying to push the car forward, but we just show it as one single force here. And remember that because the tires aren't spinning, we have good traction. That's why it's static friction. There's no sliding or anything like that. And because it's static friction, we have this, but it's not just equal to, it's equal to or less than. So the only time it's actually equal to this is if you're at that maximum extreme case where you're on the verge of slipping. In this project, we don't deal with that case. This is only assuming we have good traction. We cannot assume we're on the verge of slipping, so we cannot calculate the force using μs times n. This provides an upper limit, but we're not going to use that in this project. And you will also notice that you're not given a value for μs for your vehicle. We gave it to you in the exercise here just to illustrate for you, but you didn't actually need to use it. And when you solve the problem, you will also not need μs. So those are the three forces that result from the road. And as I said before, the only other thing touching the automobile is the air. So when you go to solve the problem, you have to think about, are there any forces due to the air touching the car? And in our class, we only deal with one. It's going to be drag. And assuming you have a significant speed, you're going to have an opposing force due to drag. And you would put that on your free body diagram, something like that. That's it. There's no other forces because there's nothing else touching the car. Sometimes students are inclined to put some kind of applied force or propulsion force on here. And because there's nothing else attached to the car, there can be no other forces. So what actually makes the car go is this friction force. It might seem a little strange, but this friction force happens because the engine's trying to make the tires spin backwards. So this friction force from the road is your propulsion force. That's the force that's actually causing the car to move. And that's the one difference from phase one, where you had a tow truck or something else attached to the car. That's why we had an applied force for that. In this case, there's nothing else attached, so your applied force is only static friction. I think that will hopefully clear up most of the confusion for you. You may have other questions, and you're welcome to contact me by email, or we can set up a meeting if you need to. But I hope that this video maybe will clarify some of the key points of confusion. So when you draw your free body diagrams in the problem, they'll all be a little different based on drag and angle, but they're pretty much going to look like this. So I'd like you, hopefully you'll at least have a good free body diagram to start with, and hopefully that'll help reduce some of your confusion. So please let me know if you have any questions. Sorry I didn't get this video out sooner, but I'm just trying to learn how all this works. But hopefully this helps you. Let me know if you have questions, and good luck.